Hey guys, hope you're doing all right, that you're happy and safe and healthy, and you're washing your hands and not touching your face, and that you're thinking a little bit about school stuff so your brain doesn't turn into soup. All right, I wanted to start off this video by addressing what appears to be a very good situation to the toilet paper crisis. However, it is not. So this is known as the redneck bidet. Do not recommend it. So several design flaws. First of all, you're going to kink the hose. And second of all, you got to have someone else turn it on. And third of all, that's not even the right water pressure. I feel like the angle's not right. That's just going to make a mess. That is a bad idea. Now this design is a little bit better. It's a little better with the shower head. You got a little more water pressure, and the sprays, I think, a little more. You got a little more precision there. However, you still gotta assemble this after you do your business, and that could be a hassle. And what if you can't reach the shower handle? That's still an issue. Do you get one of those grabby claws? Do you make an elaborate pulley system? Do you have your friend do it? I don't know. I don't know. So just go outside and use a maple leaf. Okay. So we're going to transition now to earthquakes. All right. So we know that earthquakes should occur along plate boundaries. So the red lines here show plate boundaries. And they do. They do for the most part. They're all along plate boundaries. So we should expect that at convergent plate boundaries, where plates are coming together, you're going to have the oceanic plate bending down in subduction and the continental plate bending up in a mountain range. And so that's going to create earthquakes as the plates move around. Here's the San Andreas Fault in California. As the plates slide past each other, you get earthquakes. And we also get earthquakes at hot spots. So here's the Yellowstone hotspot. There's a lot of earthquakes there as the magma rises to the surface and pushes rocks out of the way. Here's the Hawaiian hotspot. Same thing. The magma is rising and pushing earthquakes out of the way. And there are also earthquakes along ridges. They're just smaller. So here's the biggest one that happened today. It was in Nicaragua. It was a 5.2. But how do we know that that is the exact location of that earthquake? How do we know it occurred at that exact latitude and longitude? Well, first of all, we use seismographs to measure earthquakes. So basically, a seismograph is just a pen on a pendulum, and it swings back and forth. And as it swings back and forth, it makes some squiggles on a piece of paper. And the bigger the squiggles, the bigger the earthquake. And you guys can kind of make your own. Again, it's just a pendulum that makes squiggles. So there's a couple different designs to make your own. So here's what the type of information that a seismograph gives us. It's called a seismogram. So we have a time axis. So these are times. And they're given in hours, minutes, and seconds. Okay, so we have some sort of time axis. So that's so we can tell when the earthquake happened. Right, so here's 2 hours and 30 minutes. Here's 2 hours and 35 minutes. Here's 2 hours and 40 minutes. And then these squiggles represent the earthquake waves. So you've got two types of earthquake waves, actually. You have P waves and S waves. And so you can look in all of the seismographs, and you can find these two peaks in the squiggles. And the first peak is from the P wave. The second peak is from the S wave. So P waves arrive first, S waves arrive second. So that's, this P wave arrived on the bottom example here around 2 hours and 35 minutes, but this S wave over here arrived, let's see, 236, 237, 238, 239. Our S wave arrived much later, maybe like 2 hours and at a time of 2 hours and 39 minutes. So several minutes later, our S wave arrived. Right, a couple minutes later, it arrived. So the S waves arrive second. They're always slower, and because of that, we can approximate how far away each one of these seismographs is from wherever the earthquake happened. So think of it like this. You're driving down the highway and you're going like 65, and then some maniac flies past you at like 90. So the more time that goes by, the farther ahead of you that guy will be, or you could think of it as the farther behind you will be, but basically just because he's going faster than you, the more time that goes by, the bigger spacing there is between you two. So we can look at the spacing of our P and our S waves and find out how far apart they are. So for example, let's change my color here. For example, this spacing compared to this spacing, this is going to be the location that's farthest away from the epicenter. This spacing is bigger, and there are several minutes that have passed between the P and the S wave. This one's going to be close because this spacing is small, and there's only about two, a little more than 2 minutes that have passed in this case. It's only about 2 minutes past here, but like 1, 2, 3, 4 minutes past down here. And those times are very approximate. I'm not reading the scale extremely accurately here. But that's the basic idea. Actually, the one down here, this would be the closest. That's the closest distance. So that's the closest spacing between my P and S waves. So that's actually the closest. So just from looking at a couple different seismograms, we can get an idea of how close each station is. We actually need to use a chart to then get exact distances. I'll show you that in the next video.